Hello, so I'm Vikas and I've chosen the topic testing of AI accelerators. Okay, so an overview, testing AI hardware is crucial for ensuring reliability, safety and performance in critical applications, especially in the automotive and healthcare industries. It validates that the specialized hardware like GPUs and TPUs that are used can handle intense AI workloads, preventing failures which could further have severe consequences. Rigorous testing also ensures that the hardware that is built meets specific requirements, for example, speed, low latency, and accuracy. Okay, so before moving on, I would be showing the systolic array architecture, which as most papers cover, building tests for this architecture. So most AI accelerators use a systolic array structure to maximize computational efficiency. As you see here, there are a bunch of processing elements that are arranged in a parallel manner. But they are arranged in a way that they are implemented as large SoC chips, hence requiring solutions that minimize area, overhead, and test time. Okay, so the first paper that I've chosen is Structural Test Generation for AI Accelerators using Neural Twins. So the author's approach is designed to overcome the challenges of conventional ATPG, which struggle with complexity of modern integrated circuits and often require extensive backtracking to find patterns for hard to detect and random pattern resistant faults. So here you see is the original circuit and this is the generated neural twin. Okay, so I'll be explaining this paper with an example or with an analogy. So imagine trying to find a small key in a huge dark house, which is the dark house being the digital circuit, the original circuit. Conventional ATPG is like a dedicated searcher who tries to go to every single room in the house um, to find the key, which is basically in a set order, often getting stuck repeatedly by trying to same difficult corners. Backtracking. This is similar to backtracking for hard to detect faults. On the other hand, the neural twin is like a building, a miniature glowing model of the house where the presence of the key causes a dramatic color change on the roof. This is basically like a sign that the room has the key. By iteratively adjusting your input light or the input pattern in the testing analogy, the direction that makes the model grow brightest, which is again shown in the paper as gradient ascent maximization laws, you quickly identify the pattern needed to expose the key, even if it's in a tricky, unexpected location. Okay, so the final paper that I've chosen is the ZOS overhead scan for zero overhead scan for systolic array based AI accelerator. The key goal of this paper is to perform a comprehensive DFT or design for test scan while achieving zero overhead, as the name of the paper suggests, and significantly minimizing test power. The paper also achieves this by utilizing the functional circuit structure of the systolic array itself, it's avoiding the need for structural modification, adding more hardware. The fundamental mechanism of this paper relies on manipulating the weight registers in the systolic array. So there are weight registers that are shown here, are all added to each of the processing elements. This paper is significant because it is highly efficient and the results speak for it. So it achieved 100% stuck at test coverage using only 11 test patterns, which is remarkably small for generally for huge SoC chips. It demonstrates extremely low power testing, achieving a shift toggle ratio of 0.8%, which is massive reduction compared to other specialized methods. Like everything else, there is definitely some trade-off that comes with a zero area overhead because while zeros requires additional test cycles, um, which is 3n cycles compared to a normal specialized method, but these are offset by the minimal total pattern count and the significant reduction in area overhead and power consumption.